Imagine a single object shining with the brightness of 1 trillion suns, blasting out energy so intense it can be seen across the vast expanse of the universe. This isn't the stuff of science fiction, it's real, and it's called a quasar. These cosmic powerhouses are the brightest objects in the universe, and they're powered by something equally extraordinary: supermassive black holes. In this video, we're diving into the heart of these luminous giants, exploring their mind-bending energy output and the mysterious forces that drive them. You're about to see the universe in a whole new light, quite literally. So, buckle up and let's journey to the edge of the known cosmos. The cosmic lighthouses. In the vast, dark expanse of the universe, quasars stand as beacons of unimaginable brilliance. These cosmic lighthouses outshine entire galaxies, their luminosity making them visible across billions of light years. The energy they emit is staggering, often exceeding the total output of 1 trillion suns. This extreme luminosity is not due to a fleeting burst of energy, but is instead a sustained, colossal release of power. Quasars are not stars, but rather the incredibly bright centers of distant, active galaxies. At their heart lies a supermassive black hole, millions or even billions of times more massive than our Sun. As matter spirals into these black holes, it forms an accretion disk, a swirling maelstrom of gas and dust heated to incredible temperatures. This process releases an enormous amount of energy, powering the quasar's intense light and making it one of the most energetic objects in the universe. The energy output of quasars is so immense that it can outshine the combined light of every star in the galaxy that hosts them. This luminosity is not uniform, but varies over time, with some quasars exhibiting dramatic changes in brightness. These variations can occur over periods as short as hours or as long as years, providing astronomers with valuable insights into the dynamics of the accretion process. The light from quasars spans the entire electromagnetic spectrum, from radio waves to tinth rays and gamma rays. This broad spectrum of emission allows astronomers to study quasars using a variety of telescopes and instruments, each revealing different aspects of these enigmatic objects. The study of quasars has revolutionized our understanding of the early universe, galaxy formation, and the nature of black holes. Quasars act as cosmic lighthouses, guiding astronomers through the dark expanses of the universe. Their extreme luminosity makes them visible even at vast distances, providing a beacon that can be used to probe the intergalactic medium and the large-scale structure of the universe. By studying the light from quasars, astronomers can map the distribution of matter along the line of sight, revealing the cosmic web of galaxies and dark matter that permeates the universe. Quasars also serve as probes of the early universe, their light carrying information about the conditions and processes that prevailed when the universe was young. This makes them invaluable tools for understanding the evolution of galaxies and the role of supermassive black holes in shaping the cosmos. Despite their immense distance and the challenges they present, quasars continue to captivate astronomers and inspire new discoveries. A glimpse into the early universe. Quasars are among the most luminous objects in the universe, outshining entire galaxies with their intense brilliance. These cosmic beacons emit energy equivalent to the output of 1 trillion suns, making them visible across vast cosmic distances. At the heart of this extraordinary luminosity lies a supermassive black hole, millions to billions of times more massive than our Sun. As matter spirals into the black hole, it forms an accretion disk, a swirling maelstrom of superheated gas and dust. Friction and gravitational forces within this disk generate immense heat and energy, which is then radiated out as quasar light. This process is so efficient that even the most powerful nuclear reactions pale in comparison. The energy output of quasars is not just bright, it's also highly variable. Some quasars exhibit rapid fluctuations in their luminosity, changing in brightness over periods as short as hours or days. This variability provides crucial insights into the dynamics of the accretion process and the structure of the black hole's immediate environment. The sheer power of quasars can also influence their surroundings, ionizing vast clouds of gas and driving powerful outflows that shape the evolution of their host galaxies. These energetic processes make quasars invaluable tools for studying the early universe, as their light carries information about the conditions and composition of the cosmos when it was much younger. Quasars are not just bright, they are also incredibly distant. The light from the most remote quasars has traveled billions of years to reach us, offering a glimpse into the early universe. By studying these ancient beacons, astronomers can probe the conditions that prevailed when the universe was just a fraction of its current age. Quasars have been instrumental in confirming the Big Bang theory and the existence of dark matter and dark energy. Their extreme luminosity allows them to be seen at distances where normal galaxies are too faint to observe, making them vital probes of the early universe's structure and evolution. The powerhouses of the cosmos. In the vast expanse of the cosmos, quasars stand as some of the most luminous and energetic objects known to astronomers. These celestial powerhouses can outshine entire galaxies, emitting energy equivalent to the output of 1 trillion suns. The sheer brilliance of quasars is a spectacle of cosmic proportions, a beacon of light that can be observed from billions of light-years away. At the heart of this extraordinary luminosity lies a supermassive black hole, a gravitational behemoth that powers the quasar's radiant display. The energy output of quasars is nothing short of astonishing. These cosmic giants emit radiation across the electromagnetic spectrum, from radio waves to X rays and gamma rays. The immense energy is generated as matter, in the form of gas and dust, spirals into the supermassive black hole at the quasar's core. This process, known as accretion, releases an enormous amount of gravitational energy, which is then converted into light and other forms of radiation. The resulting luminosity is so intense that it can outshine the combined light of all the stars in the quasar's host galaxy. Quasars are not merely passive observers in the cosmic ballet. They actively shape their surroundings, influencing the evolution of galaxies and the intergalactic medium. The powerful jets of energy and matter that quasars emit can extend for thousands of light years, interacting with the surrounding gas and triggering star formation. These jets, often referred to as relativistic jets, are composed of charged particles accelerated to near the speed of light. The interaction between these jets and the interstellar medium can create complex structures, such as radio lobes and hotspots, which are visible in radio and X-ray observations. The study of quasars has provided astronomers with valuable insights into the nature of supermassive black holes and the early universe. Quasars are believed to be the active nuclei of distant, young galaxies, offering a glimpse into the conditions that prevailed in the early cosmos. By observing quasars, scientists can probe the properties of supermassive black holes, such as their mass, spin, and accretion rates. Moreover, quasars serve as cosmic lighthouses, illuminating the intergalactic medium and revealing the distribution of matter on the largest scales. The information gleaned from these studies not only deepens our understanding of the universe, but also fuels our curiosity to explore the mysteries that lie beyond. Quasars, not your average star. In the vast expanse of the universe, quasars stand out as some of the most extraordinary and enigmatic objects. They are not your average stars, but rather, they are the incredibly luminous centers of distant, active galaxies. Quasars emit more energy than entire galaxies, making them visible from billions of light-years away. This immense luminosity is not due to the fusion of hydrogen atoms, as in stars, but rather, it is powered by the accretion of material into supermassive black holes at the hearts of these galaxies. The energy output is so immense that a single quasar can outshine 1 trillion stars combined. The process that drives this extraordinary luminosity is complex and fascinating. As matter falls into the supermassive black hole, it forms an accretion disk, a swirling maelstrom of gas and dust heated to extreme temperatures. This heated material emits a tremendous amount of radiation across the electromagnetic spectrum, from radio waves to X rays and gamma rays. Additionally, some of the infalling material is ejected in powerful jets perpendicular to the accretion disk, creating beams of intense radiation that can stretch for thousands of light years. These jets are a hallmark of active galactic nuclei and contribute significantly to the overall luminosity of quasars. Quasars are not static objects. They exhibit significant variability in their brightness over time. This variability can occur on timescales ranging from hours to years, providing valuable insights into the physical processes occurring near the black hole. The rapid changes in brightness suggest that the emission region is relatively small, likely within a few light days of the black hole. This variability, combined with the extreme luminosity, makes quasars invaluable tools for studying the properties of supermassive black holes and their environments. The discovery of quasars has revolutionized our understanding of the universe. Initially, their extreme redshifts and point-like appearance led astronomers to believe they were nearby stars. However, further observations revealed their true nature as distant, incredibly luminous objects. This realization has profound implications for our understanding of galaxy formation and evolution. Quasars are now recognized as a crucial phase in the life cycle of galaxies, particularly in the early universe. Their study provides a window into the conditions and processes that shape the cosmos as we know it today. The birth of a quasar. In the vast expanse of the cosmos, quasars stand as the most luminous objects, outshining entire galaxies. Their extreme brightness is a result of the immense energy output, which can be 1,000 times greater than that of a typical galaxy. This staggering luminosity is powered by supermassive black holes, which reside at the centers of galaxies. These black holes, with masses millions or even billions of times that of our Sun, act as cosmic engines, driving the incredible energy output of quasars. The process begins with a vast accretion disk of gas and dust swirling around the black hole. As this material spirals inward, it heats up due to friction and gravitational forces, reaching temperatures so high that it emits intense radiation across the electromagnetic spectrum. This radiation is what we observe as the quasar's light. The birth of a quasar is a dramatic event, often triggered by significant disturbances in the galaxy. These disturbances can be mergers with other galaxies, collisions, or even the influx of large amounts of gas and dust. Such events fuel the supermassive black hole, causing it to become incredibly active. As more material falls into the black hole, the accretion disk becomes brighter and hotter, leading to the formation of a quasar. The energy output is so immense that it can outshine the combined light of all the stars in the host galaxy. This makes quasars visible from vast distances, even across the entire observable universe. Their light can travel billions of light years, providing astronomers with a powerful tool to study the early universe. Quasars are not static objects. Their brightness can vary over time. This variability is thought to be due to changes in the accretion rate of material into the black hole. When more material falls in, the quasar becomes brighter, and when less material falls in, it dims. This variability can occur on timescales ranging from hours to years, depending on the size of the accretion disk and the rate of infall. The study of quasar variability provides valuable insights into the physics of accretion disks and the behavior of supermassive black holes. It also helps astronomers understand the role of quasars in galaxy evolution and the intergalactic medium. The energy output of quasars is not just limited to visible light. They emit radiation across the entire electromagnetic spectrum, from radio waves to gamma rays. This makes them detectable by a wide range of astronomical instruments. The study of quasar spectra reveals a wealth of information about the composition, velocity, and distance of the emitting material. For instance, the presence of broad emission lines in quasar spectra indicates the presence of high-velocity gas near the black hole. The study of these lines provides clues about the dynamics of the accretion disk and the processes driving the quasar's energy output. Moreover, the redshift of quasar spectra allows astronomers to determine their distance and study the large-scale structure of the universe. Supermassive black holes, the engine behind the light. In the vast expanse of the cosmos, quasars stand as some of the most luminous objects, outshining entire galaxies. Their brilliance is not born from stars, but from the insatiable hunger of supermassive black holes. These cosmic behemoths, millions to billions of times more massive than our Sun, reside at the centers of galaxies. As matter spirals into these black holes, it forms an accretion disk, a swirling maelstrom of gas and dust heated to incredible temperatures. This process releases an enormous amount of energy, making quasars visible across vast cosmic distances. The energy output of quasars is staggering. A single quasar can emit more light than 1 trillion stars combined. This luminosity is not steady but can vary over time, with some quasars exhibiting dramatic fluctuations. The power behind this light show is the conversion of gravitational energy into heat and light as matter falls into the black hole. Not all the infalling material makes it into the black hole. Some is ejected in powerful jets perpendicular to the accretion disk. These jets, traveling at nearly the speed of light, can extend for thousands of light years, further contributing to the quasar's brilliance. Quasars are not just bright, they are also energetic across the entire electromagnetic spectrum. They emit radiation from radio waves to gamma rays, making them detectable by various telescopes. The study of quasars has provided valuable insights into the early universe, as their light has traveled billions of years to reach us. By observing quasars, astronomers can probe the conditions of the universe when it was much younger. The extreme environments around supermassive black holes also serve as natural laboratories for testing theories of physics under extreme conditions. The discovery of quasars has revolutionized our understanding of the universe. Initially, their nature was a mystery, with some scientists proposing exotic explanations. However, as observational techniques improved, the connection between quasars and supermassive black holes became clear. Today, quasars are recognized as crucial components in the evolution of galaxies. Their immense energy output can influence the formation of stars and the overall structure of their host galaxies. By studying quasars, astronomers gain a deeper understanding of the cosmic processes that shape the universe. Feeding the beast, accretion disks. Quasars are among the most luminous objects in the universe, outshining entire galaxies with their intense energy output. At the heart of these cosmic beacons lies a supermassive black hole, millions or even billions of times more massive than our Sun. These black holes are not just passive entities. They are active, voracious consumers of gas and dust, and it is this feeding process that powers the extraordinary luminosity of quasars. The energy released is so immense that it can be observed across vast cosmic distances, making quasars visible even from the early universe. The process begins with an accretion disk, a swirling, flattened structure of gas and dust that forms around the black hole. This disk is not a calm, orderly place. Instead, it is a chaotic, dynamic environment where matter is heated to extreme temperatures due to friction and gravitational forces. As the material spirals inward, it releases an enormous amount of energy, primarily in the form of electromagnetic radiation. This radiation spans the entire spectrum, from radio waves to 10th rays and gamma rays, contributing to the quasar's brilliant display. The accretion disk itself can extend for millions of miles, and its temperature can reach tens of thousands of degrees, making it one of the hottest places in the universe. Not all the material in the accretion disk makes it into the black hole. Some of it is ejected in powerful jets that shoot out perpendicular to the disk, creating spectacular displays of cosmic fireworks. These jets, driven by the black hole's magnetic fields, can extend for thousands of light years and are visible in various wavelengths of light. They play a crucial role in regulating the growth of the black hole and influencing the evolution of the surrounding galaxy. The energy output from these jets can be so intense that it can heat and ionize the interstellar medium, affecting star formation and galaxy evolution on a large scale. The luminosity of quasars is not constant. It varies over time. This variability is thought to be due to changes in the accretion rate, as well as instabilities within the accretion disk itself. By studying these variations, astronomers can gain insights into the physical processes occurring near the black hole. Quasars are also valuable tools for probing the early universe. Their light has traveled billions of years to reach us, providing a glimpse into the conditions and structures that existed when the universe was young. This makes them invaluable for understanding the formation and evolution of galaxies, as well as the role of supermassive black holes in shaping the cosmos. Jets, the cosmic fireworks. Quasars are among the most luminous objects in the universe, outshining entire galaxies with their intense brilliance. At their core, they are powered by supermassive black holes, which are millions or even billions of times more massive than our Sun. These black holes reside at the centers of galaxies, and as they consume surrounding matter, they release an enormous amount of energy. This process creates a phenomenon known as an accretion disk, a swirling maelstrom of gas and dust that heats up to extreme temperatures, emitting light across the electromagnetic spectrum. The energy output is so immense that quasars can be observed from billions of light years away, making them invaluable tools for studying the early universe. One of the most spectacular features of quasars is their ability to produce powerful jets of plasma that shoot out at nearly the speed of light. These jets, often referred to as cosmic fireworks, are a direct result of the intense magnetic fields and rotational energy of the supermassive black hole. As matter spirals inward, it becomes highly ionized and accelerated along the black hole's magnetic field lines, eventually being ejected in narrow beams perpendicular to the accretion disk. These jets can extend for thousands of light years, creating vast, glowing structures that can be seen in radio, optical, and 10th-ray wavelengths. The energy carried by these jets is so immense that they can influence the evolution of their host galaxies, triggering star formation or, conversely, halting it by heating and dispersing the gas. The luminosity of quasars is truly mind-boggling. A single quasar can emit more energy than 1 trillion stars combined. This staggering output is due to the efficient conversion of gravitational energy into radiation as matter falls into the black hole. The accretion process is not smooth. Instead, it is marked by violent fluctuations and outbursts. These variations can cause the quasar's brightness to change dramatically over short periods, a phenomenon known as variability. Observing these changes helps astronomers understand the dynamics of the accretion disk and the mechanisms driving the jets. The jets themselves are not uniform. They often exhibit complex structures, including knots, hotspots, and shocks, which reveal the intricate interplay of magnetic fields, relativistic particles, and the surrounding interstellar medium. In addition to their intrinsic fascination, quasar jets provide a unique laboratory for studying fundamental physics under extreme conditions. The particles in these jets are accelerated to energies far beyond what can be achieved in Earth-based accelerators. This makes them ideal for probing the limits of particle physics and testing theories of relativity and magnetohydrodynamics. Furthermore, the interaction of these jets with the intergalactic medium can create massive shock waves and bubbles of hot gas, which in turn can influence the large-scale structure of the universe. By studying these phenomena, astronomers gain insights into the cosmic web of galaxies and the role of active galactic nuclei in shaping the universe as we know it. The study of quasar jets is a vibrant and rapidly evolving field, offering a glimpse into the most energetic processes in the cosmos. The brightest beacons. Quasars are among the most luminous objects in the universe, outshining entire galaxies with their intense brilliance. These cosmic powerhouses emit energy across the electromagnetic spectrum, from radio waves to 10th rays, with some quasars shining with the luminosity of 1 trillion suns. The sheer scale of their energy output is staggering, making them visible from vast cosmic distances. This extreme luminosity is not a fleeting phenomenon, but a sustained display of power, driven by the insatiable appetite of supermassive black holes at their cores. At the heart of every quasar lies a supermassive black hole, millions to billions of times more massive than our Sun. As matter in the form of gas, dust, and stars spirals into the black hole, it forms an accretion disk, a swirling, superheated maelstrom of material. The friction and gravitational forces within this disk generate immense heat and energy, which is then radiated outward as light and other forms of electromagnetic radiation. This process is so efficient that a significant portion of the matter's mass is converted into energy, in accordance with Einstein's famous equation E=mc². The result is a brilliant beacon that can outshine the combined light of all the stars in the quasar's host galaxy. The energy output of quasars is not uniform. It varies over time, with some quasars exhibiting dramatic fluctuations in brightness. These variations can occur on timescales ranging from hours to years, providing astronomers with valuable insights into the dynamics of the accretion process. The most luminous quasars, known as hyperluminous quasars, can emit energy at rates that defy easy comprehension. For instance, the quasar SDSS J0100+2802 25.8, located approximately 12.8 billion light-years away, holds the record for the most luminous known quasar, with an energy output equivalent to 420 trillion suns. Such extreme luminosity is a testament to the incredible forces at play within these cosmic engines. Quasars are not merely passive beacons, they actively shape their surroundings. The intense radiation and particle winds they emit can influence the evolution of their host galaxies, regulating star formation and even clearing out interstellar material. This feedback mechanism is crucial for understanding the coevolution of supermassive black holes and their host galaxies. Despite their immense distance from Earth, quasars serve as vital probes for studying the early universe, offering glimpses into the conditions and processes that prevailed when the cosmos was still in its infancy. Their study continues to push the boundaries of our knowledge, revealing the profound and often enigmatic nature of the universe. A dance of light and shadow. In the vast expanse of the cosmos, quasars reign as the brightest beacons, outshining entire galaxies. These celestial powerhouses are not stars, but rather the active hearts of distant galaxies, powered by supermassive black holes. At their core, quasars are a mesmerizing dance of light and shadow, a cosmic ballet where matter and energy intertwine in a spectacular display. The energy output of a single quasar can be 1,000 times greater than that of our entire Milky Way galaxy. This staggering luminosity is not a gentle glow but a fierce, high-energy radiation that spans the electromagnetic spectrum, from radio waves to tinth rays and gamma rays. The driving force behind this extreme luminosity is the supermassive black hole at the quasar's center. As matter, in the form of gas, dust, and stars, spirals into the black hole, it forms an accretion disk, a swirling, superheated maelstrom of material. The intense gravitational forces and friction within the disk heat the matter to millions of degrees, causing it to emit an enormous amount of light and energy. This process is not steady but rather a dynamic, chaotic dance. The black hole's immense gravity bends and twists the light, creating a shadow that dances in tandem with the radiant accretion disk. Jets of high-energy particles, often extending thousands of light-years, shoot out from the poles of the black hole, adding to the quasar's brilliance. The energy output of quasars is so immense that it can be detected across billions of light-years. Despite their distance, quasars appear as point sources of light, much like stars, but their spectra reveal their true nature. The light from quasars is not constant, but varies over time, reflecting the turbulent processes occurring near the black hole. These variations can happen on timescales as short as hours or days, providing astronomers with a cosmic clock to study the dynamics of these distant objects. The study of quasars has revealed much about the early universe, as their light has traveled for billions of years to reach us, offering a glimpse into the cosmos' formative years. The dance of light and shadow in quasars is a testament to the extreme physics at play near supermassive black holes. The interplay of matter, energy, and gravity creates a spectacle that challenges our understanding of the universe. Quasars are not just distant lighthouses, but also cosmic laboratories, where the laws of physics are pushed to their limits. By studying these enigmatic objects, astronomers hope to unravel the mysteries of black holes, galaxy formation, and the evolution of the universe itself. The dance continues, a cosmic ballet that has been playing out for billions of years, and we are fortunate to be spectators to this awe-inspiring performance. The spectrum of quasars. Quasars are among the most luminous objects in the universe, outshining entire galaxies despite their relatively small size. This extraordinary brightness is attributed to the accretion disks of supermassive black holes, which can be millions or even billions of times more massive than our Sun. As matter spirals into these black holes, it forms a swirling, superheated disk that emits immense amounts of energy across the electromagnetic spectrum. The energy output is so vast that quasars can be observed from Earth even though they are located at cosmological distances, often billions of light-years away. The spectrum of quasars is a rich tapestry of information, revealing their extreme conditions and the processes driving their luminosity. When astronomers analyze the light from quasars, they observe a continuous spectrum with prominent emission lines superimposed. These lines are characteristic of highly ionized gas, indicating temperatures reaching millions of degrees. The broad emission lines, in particular, are a hallmark of quasars, arising from gas moving at high velocities near the black hole. This Doppler broadening provides clues about the dynamics of the accretion disk and the central engine powering the quasar. In addition to emission lines, quasars exhibit strong absorption features, which can be used to probe the intergalactic medium along the line of sight. These absorption lines are caused by gas clouds between the quasar and the observer, and they provide valuable insights into the composition, density, and distribution of matter in the early universe. By studying these features, astronomers can map the large-scale structure of the cosmos and trace the evolution of galaxies over time. The spectrum of quasars, therefore, serves as a powerful tool for understanding both the immediate environment of these enigmatic objects and the broader context of cosmic evolution. The energy output of quasars is not uniform across the spectrum. While they emit strongly in the optical and ultraviolet bands, they also produce significant amounts of X rays and even gamma rays. This broad spectrum of emission is a direct consequence of the extreme conditions near the supermassive black hole. The accretion disk itself emits thermal radiation, while the corona, a region of hot plasma above the disk, produces X rays through processes like inverse Compton scattering. The jet, a narrow stream of particles ejected at relativistic speeds, can also contribute to the high-energy emission. Together, these components create a complex and dynamic spectrum that challenges our understanding of astrophysical processes. Redshifts, measuring the distance. Quasars are among the most luminous objects in the universe, outshining entire galaxies with their intense energy output. This staggering luminosity is believed to be powered by supermassive black holes, which reside at the centers of galaxies. As matter falls into these black holes, it forms an accretion disk, a swirling maelstrom of gas and dust heated to incredible temperatures. The energy released from this process is so immense that it can outshine the combined light of billions of stars. Quasars are not just bright, they are beacons of energy, emitting radiation across the electromagnetic spectrum, from radio waves to X rays. To understand the scale of a quasar's energy output, consider that a single quasar can emit up to 1,000 times the energy of a typical galaxy. This energy is not just light, but also includes powerful jets of particles that can extend for thousands of light years. These jets, often referred to as relativistic jets, are a direct result of the black hole's immense gravitational pull and the resulting acceleration of particles. The energy output is so extreme that it can influence the evolution of the entire host galaxy, shaping its structure and even triggering star formation in distant regions. Measuring the distance to quasars is a complex task, but it is crucial for understanding their properties and the universe's structure. Astronomers use a phenomenon called redshift to determine these distances. Redshift occurs when light from an object is stretched to longer wavelengths as the object moves away from the observer. This effect is a result of the expansion of the universe, which causes distant objects to recede from us at high velocities. By measuring the redshift of a quasar's light, scientists can calculate its distance. The greater the redshift, the farther away the quasar is. The redshift of a quasar is typically measured by analyzing its spectral lines, which are unique patterns of light emitted or absorbed by the quasar's gas. These lines shift to longer wavelengths as the quasar moves away. For example, a quasar with a high redshift, such as 6.4, indicates that it is extremely distant, likely formed in the early universe. By studying these redshifts, astronomers can map the distribution of quasars and gain insights into the large-scale structure of the cosmos. This information is invaluable for understanding the universe's evolution and the role of supermassive black holes in shaping galaxies. Quasars and the expansion of the universe. Quasars are among the most enigmatic and powerful objects in the universe, their extreme luminosity outshining entire galaxies. This staggering energy output is not generated by stars, but by supermassive black holes, which lurk at the centers of distant galaxies. These black holes, with masses millions or even billions of times that of our Sun, accrete vast amounts of gas and dust. As this material spirals inward, it forms an accretion disk, heating up to incredible temperatures and emitting intense radiation across the electromagnetic spectrum. The energy released is so immense that quasars can be observed billions of light years away, making them vital tools for studying the early universe. The light from quasars doesn't just travel vast distances, it carries with it crucial information about the expansion of the universe. By measuring the redshift of quasar light, astronomers can determine how much the universe has expanded since the light was emitted. This redshift is a direct consequence of the universe's expansion, causing the wavelengths of light to stretch and shift toward the red end of the spectrum. Quasars, being so luminous, provide a bright and distant beacon that allows scientists to probe the cosmos's expansion over immense scales. Their light has traversed such vast distances that it offers a snapshot of the universe's state billions of years ago, providing a unique window into cosmic history. Moreover, quasars play a pivotal role in mapping the large-scale structure of the universe. Their distribution and properties can reveal the underlying cosmic web of galaxies and dark matter. By studying quasars, astronomers can trace the filamentary structures that connect galaxies and understand how matter is distributed on the largest scales. This information is invaluable for testing theories of cosmic inflation and the nature of dark energy, the mysterious force driving the accelerated expansion of the universe. Quasars, with their extreme luminosity and distant nature, serve as cosmic lighthouses, illuminating the path to a deeper understanding of the universe's expansion and evolution. The role of quasars in galaxy formation. Quasars are among the most luminous objects in the universe, outshining entire galaxies with their intense energy output. At their core, quasars are powered by supermassive black holes, which are millions or even billions of times more massive than our Sun. These black holes reside at the centers of galaxies and accrete vast amounts of gas and dust, forming an accretion disk. As material spirals inward, it heats up due to friction and gravitational forces, emitting enormous amounts of radiation across the electromagnetic spectrum. This process releases energy equivalent to the output of 1,000 or more galaxies, making quasars visible from billions of light years away. The energy emitted by quasars is not uniform. It varies across different wavelengths. They are particularly bright in the 10th ray and ultraviolet parts of the spectrum, but they also emit visible light, radio waves, and even gamma rays. The sheer power of quasars can be attributed to the efficient conversion of gravitational energy into radiation. As matter falls into the black hole, it releases energy in the form of light and heat, creating the brilliant display characteristic of quasars. This energy output is so immense that it can influence the surrounding galaxy, shaping its evolution and structure. Quasars play a crucial role in galaxy formation and evolution. Their intense radiation and powerful jets can heat and disperse gas, affecting star formation rates. In some cases, the energy output from a quasar can halt the formation of new stars by blowing away the gas and dust that would otherwise collapse to form stars. This regulatory effect is known as feedback, and it helps to explain why some galaxies stop forming stars prematurely. Additionally, the jets emitted by quasars can interact with the intergalactic medium, enriching it with heavy elements and influencing the growth of other galaxies. The study of quasars provides valuable insights into the early universe. Since their light has traveled billions of years to reach us, observing quasars allows astronomers to peer back in time and study the conditions of the young universe. This helps in understanding how galaxies formed and evolved over cosmic time. Quasars also serve as beacons for studying the large-scale structure of the universe, as their light is absorbed and scattered by intervening gas and dust, revealing the distribution of matter along the line of sight. By analyzing the spectra of quasars, scientists can map the cosmic web of galaxies and dark matter, providing a deeper understanding of the universe's structure and evolution. Active galactic nuclei, the quasar's cousin. In the vast expanse of the cosmos, quasars reign as the brightest objects, outshining entire galaxies. These celestial powerhouses are fueled by supermassive black holes, which reside at the centers of galaxies. The energy output of a single quasar can be 1,000 times greater than that of our Milky Way. This immense luminosity is a result of the accretion process, where gas and dust swirl into the black hole, forming a glowing, hot disk. The gravitational energy of the infalling material is converted into light, making quasars visible across billions of light years. Quasars are not solitary phenomena. They are part of a broader family of objects known as active galactic nuclei, AGN. AGN are the compact regions at the centers of galaxies that emit immense amounts of radiation. They are the quasar's cousin, sharing similar characteristics but differing in their energy output and appearance. While quasars are the most luminous AGN, others may be less bright, but still exhibit powerful emissions. The diversity within the AGN family is vast, with some emitting jets of plasma, others displaying rapid variability, and a few showing broad emission lines in their spectra. The extreme luminosity of quasars and AGN is a testament to the incredible processes occurring around supermassive black holes. As matter spirals inward, it forms an accretion disk, which heats up due to friction and gravitational forces. This disk can reach temperatures of millions of degrees, emitting 10th rays and other forms of high-energy radiation. Additionally, some AGN launch powerful jets perpendicular to the accretion disk, accelerating particles to nearly the speed of light. These jets can extend for thousands of light years, creating vast, glowing structures visible across the universe. Understanding quasars and AGN provides insights into the growth and evolution of galaxies. The energy they emit can influence star formation, regulate the growth of the central black hole, and even shape the intergalactic medium. By studying these objects, astronomers gain a deeper understanding of the fundamental processes that govern the cosmos. The study of AGN is a dynamic and evolving field, with new discoveries continually reshaping our understanding of these enigmatic objects. From the brightest quasars to the more subdued AGN, these celestial phenomena offer a window into the most energetic processes in the universe. From quasars to blazars, a family of objects. Quasars are among the most luminous objects in the universe, outshining entire galaxies despite their relatively small size. They emit energy across the electromagnetic spectrum, from radio waves to 10th rays, with some quasars being visible in the visible spectrum as well. This immense energy output is thought to be powered by supermassive black holes, which reside at the centers of galaxies. As matter falls into these black holes, it forms an accretion disk, a swirling maelstrom of gas and dust that heats up due to friction and gravitational forces, releasing enormous amounts of energy. This process is so efficient that a single quasar can emit up to 1,000 times the energy of a typical galaxy. For instance, the quasar 3C273, one of the brightest known, has an absolute magnitude of 26.7, making it visible despite being over 2 billion light-years away. The family of objects that includes quasars also encompasses blazars, which are even more extreme in their properties. Blazars are a subset of quasars, but with a key difference. Their jets of high-energy particles are pointed directly towards the Earth. This alignment makes blazars appear exceptionally bright and variable as we observe the jet's emissions head-on. The energy output from blazars can fluctuate dramatically over short periods, sometimes varying in brightness by a factor of 10 within hours or even minutes. This variability is a direct result of the jet's orientation and the chaotic nature of the accretion process. Blazars are also known for their high-energy gamma-ray emissions, which are produced as the jet particles interact with the surrounding medium and radiation fields. The relationship between quasars and blazars is a testament to the diversity of active galactic nuclei, AGN. AGN are the compact regions at the centers of galaxies that emit vast amounts of energy, and they come in various flavors, including quasars, blazars, safer galaxies, and radio galaxies. The differences between these types of AGN are largely due to orientation effects and the viewing angle from Earth. For example, if the jet of an AGN is pointed away from us, it might appear as a relatively dim radio galaxy. However, if the jet is pointed towards us, it becomes a blazar, one of the most energetic and variable objects in the universe. This orientation-dependent classification helps astronomers understand the underlying physics of these objects and the role they play in galaxy evolution. The study of quasars and blazars has provided profound insights into the nature of supermassive black holes and their environments. By observing the emissions from these objects, astronomers can probe the physics of accretion disks, jet formation, and the interplay between black holes and their host galaxies. For instance, the study of quasars has revealed that supermassive black holes can influence the evolution of their host galaxies through feedback mechanisms, such as heating the interstellar medium and regulating star formation. Blazars, with their extreme properties, offer a unique laboratory for studying particle acceleration and high-energy astrophysics. The energy output from blazars can be so intense that it can ionize the intergalactic medium, affecting the large-scale structure of the universe. The life cycle of a quasar. Quasars are among the most luminous objects in the universe, outshining entire galaxies with their intense energy output. At their core, quasars are powered by supermassive black holes, which are millions or even billions of times more massive than our Sun. These black holes reside at the centers of galaxies and are surrounded by accretion disks, swirling masses of gas and dust that heat up to incredible temperatures as they spiral inward. The gravitational energy released by this process is so immense that it generates the extraordinary luminosity characteristic of quasars. This energy is not just visible light, but spans the entire electromagnetic spectrum, from radio waves to 10th rays and gamma rays. The sheer power of a quasar can be so great that it outshines the combined light of all the stars in its host galaxy, making it visible across vast cosmic distances. The life cycle of a quasar begins with the formation of a supermassive black hole at the center of a galaxy. As the black hole grows by accreting matter, the surrounding accretion disk becomes increasingly dense and hot. This process triggers the quasar phase, during which the black hole emits enormous amounts of energy. The quasar's brightness is not constant. It can vary over time due to changes in the accretion rate or the interaction with nearby matter. Over millions of years, the quasar's energy output can deplete the surrounding gas and dust, eventually leading to a decline in its luminosity. This marks the transition from an active quasar to a more quiescent state, where the black hole continues to exist but emits far less energy. The quasar phase is a fleeting moment in the life of a galaxy, but it plays a crucial role in shaping the galaxy's evolution. During its active phase, a quasar can have a profound impact on its host galaxy and the surrounding intergalactic medium. The intense radiation and particle jets emitted by the quasar can heat and disperse gas, potentially halting star formation in the galaxy. This feedback mechanism is thought to regulate the growth of galaxies and their central black holes, creating a balance that prevents the galaxy from becoming too massive. The energy output of a quasar can also ionize the intergalactic medium, contributing to the reionization of the universe after the cosmic dark ages. Despite their ephemeral nature, quasars leave a lasting imprint on the cosmos, influencing the structure and evolution of galaxies over billions of years. Their study provides valuable insights into the fundamental processes that govern the universe. The death of a quasar, fading into obscurity. Quasars are among the most luminous objects in the universe, outshining entire galaxies with their intense brilliance. These cosmic beacons are powered by supermassive black holes, which reside at the centers of distant galaxies. As matter spirals into these black holes, it forms an accretion disk, a swirling maelstrom of gas and dust heated to incredible temperatures. This process releases enormous amounts of energy, making quasars visible across vast cosmic distances. Their luminosity can be 1,000 times greater than that of a typical galaxy, making them appear as bright, star-like points of light in the night sky. The energy output of quasars is staggering. They emit radiation across the electromagnetic spectrum, from radio waves to 10th rays and gamma rays. This radiation is a byproduct of the immense gravitational forces at play, as matter is compressed and heated to extreme temperatures before being consumed by the black hole. The light from quasars can travel billions of light years, providing astronomers with a glimpse into the early universe. Despite their brilliance, quasars are not eternal. Their lifespans are relatively short on cosmic scales, typically lasting only a few million years. As a quasar's fuel supply diminishes, its luminosity begins to fade. The accretion disk, once a vibrant, energetic disk of matter, starts to thin out. With less material to feed on, the supermassive black hole's activity wanes. This gradual decline marks the beginning of the quasar's end. Over time, the once bright quasar fades into obscurity, becoming a quiet, dormant black hole at the center of a galaxy. This transformation is a natural part of the life cycle of active galactic nuclei, including quasars. The fading of a quasar is a complex process influenced by various factors. One key factor is the depletion of the surrounding gas and dust. Without a steady supply of matter, the accretion disk cannot sustain its high levels of activity. Additionally, feedback mechanisms, such as powerful jets and winds, can expel material from the vicinity of the black hole, further reducing the available fuel. As the quasar's luminosity decreases, it becomes less visible to astronomers, eventually blending into the background of the universe. This transition from a brilliant quasar to a quiescent black hole is a testament to the dynamic and ever-changing nature of the cosmos. Quasars and gravitational lensing. Quasars are among the most luminous objects in the universe, outshining entire galaxies with their intense energy output. This staggering luminosity is believed to be powered by supermassive black holes, which reside at the centers of galaxies. These black holes, with masses millions or even billions of times that of the Sun, accrete vast amounts of gas and dust from their surroundings. As this material spirals inwards, it forms an accretion disk, where it heats up due to friction and gravitational forces, emitting immense amounts of radiation across the electromagnetic spectrum. The energy released is so profound that it can outshine the combined light of all the stars in the host galaxy. This process also generates powerful jets of plasma that shoot out perpendicular to the accretion disk, further contributing to the quasar's brightness. Gravitational lensing occurs when a massive object, such as a galaxy or a cluster of galaxies, bends the path of light from a more distant object, like a quasar, due to its gravitational field. This effect, predicted by Einstein's theory of general relativity, can magnify and distort the image of the quasar, creating multiple images or a ring-like structure around the lensing object. This phenomenon not only provides a natural telescope to observe distant quasars, but also offers a unique opportunity to study the distribution of dark matter in the lensing object. By analyzing the lensed images, astronomers can infer the mass and structure of the intervening galaxy or cluster, shedding light on the mysterious nature of dark matter. The combination of quasars and gravitational lensing has led to groundbreaking discoveries in astrophysics. For instance, lensed quasars have been used to measure the expansion rate of the universe, known as the Hubble constant, with unprecedented precision. Moreover, the time delays between the multiple images of a lensed quasar can provide insights into the structure and evolution of the quasar itself. These time delays occur because the light from different images travels along slightly different paths, experiencing varying gravitational potentials. By monitoring these delays, astronomers can probe the inner workings of quasars, such as the size of the accretion disk and the dynamics of the central black hole. In addition to their scientific value, lensed quasars offer a spectacular display of cosmic beauty. The distorted and magnified images of quasars, often appearing as arcs or rings around the lensing galaxy, are a testament to the awe-inspiring nature of the universe. These images not only captivate the imagination, but also serve as a reminder of the intricate interplay between gravity and light. As our understanding of quasars and gravitational lensing continues to grow, so too does our appreciation for the wonders of the cosmos. The study of these phenomena not only expands the boundaries of human knowledge, but also inspires a sense of wonder and curiosity about the universe we inhabit. The future of quasar research. Quasars are among the most enigmatic and powerful objects in the universe, outshining entire galaxies with their extreme luminosity. These cosmic beacons are powered by supermassive black holes, which reside at the centers of distant galaxies. As matter spirals into these black holes, it forms an accretion disk, a swirling maelstrom of gas and dust heated to incredible temperatures. This process releases an enormous amount of energy, making quasars visible across vast cosmic distances. The energy output of a single quasar can be 1,000 times greater than that of our entire Milky Way galaxy. This luminosity is so intense that it can outshine the combined light of all the stars in the quasar's host galaxy, making them appear as point sources of light in the night sky. The future of quasar research is poised to unlock even greater mysteries about the early universe and the nature of black holes. Advances in telescope technology, such as the James Webb Space Telescope, JWST, are allowing astronomers to observe quasars in unprecedented detail. JWST's infrared capabilities enable scientists to peer through dusty regions of the universe, revealing quasars that were previously hidden from view. This will provide insights into the formation and evolution of supermassive black holes, as well as their role in galaxy formation. Additionally, upcoming missions like the European Space Agency's Euclid Telescope and the ground-based Extremely Large Telescope, YELT, will further enhance our ability to study quasars. These instruments will allow astronomers to measure the masses of supermassive black holes with greater precision and to study the dynamics of the accretion disks that power quasars. One of the most exciting aspects of quasar research is the potential to use them as cosmic lighthouses to probe the intergalactic medium. Quasars emit light that travels billions of light years before reaching Earth, passing through clouds of gas and dust along the way. By analyzing the spectra of quasar light, astronomers can map the distribution and composition of these intergalactic clouds. This information provides valuable clues about the large-scale structure of the universe and the processes that govern galaxy formation. Furthermore, quasars can serve as probes for studying the early universe, offering a glimpse into the conditions that prevailed just a few 100 million years after the Big Bang. As our understanding of quasars deepens, so too will our knowledge of the fundamental forces and particles that shape the cosmos. The study of quasars also holds promise for testing the limits of general relativity and exploring the nature of dark energy. The extreme gravitational fields around supermassive black holes provide a unique laboratory for testing Einstein's theory of gravity. By observing the orbits of stars and gas clouds near quasars, astronomers can look for deviations from the predictions of general relativity. Additionally, quasars can be used to measure the expansion rate of the universe, which is crucial for understanding the role of dark energy in cosmic acceleration. As our observational capabilities continue to improve, quasars will remain at the forefront of astrophysical research, shedding light on some of the most profound questions in science. Unraveling the mysteries of quasars. Quasars are among the most enigmatic and powerful objects in the universe. They are incredibly luminous, outshining entire galaxies despite their relatively small size. This extreme brightness is not due to a large number of stars, but rather a singular, extraordinarily energetic process. At the heart of every quasar lies a supermassive black hole, millions or even billions of times more massive than our Sun. As matter spirals into these black holes, it forms an accretion disk, a swirling maelstrom of gas and dust heated to incredible temperatures. This process releases an enormous amount of energy, making quasars visible across vast cosmic distances. The energy output of quasars is staggering. They can emit up to 1,000 times the energy of a typical galaxy, and their luminosity can vary dramatically over short periods. This variability is a key clue to their nature, suggesting that the energy is not coming from a steady process like star formation, but rather from the chaotic and dynamic environment around a supermassive black hole. The light from quasars spans the entire electromagnetic spectrum, from radio waves to tinth rays and gamma rays. This broad spectrum provides astronomers with a wealth of data to study these cosmic beacons. Quasars are not just bright, they are also incredibly distant. The light from the most distant quasars has traveled billions of light years to reach us, offering a glimpse into the early universe. This makes quasars valuable tools for probing the cosmos. By studying their light, scientists can learn about the intergalactic medium, the large-scale structure of the universe, and even the nature of dark matter and dark energy. The extreme conditions around quasars also provide a natural laboratory for testing theories of physics under conditions that cannot be replicated on Earth. Despite their brightness, quasars are not easy to study. Their small size and immense distance make them challenging targets for telescopes. However, advances in technology and observational techniques have allowed astronomers to make significant progress in understanding these cosmic powerhouses. For example, the Hubble Space Telescope has captured detailed images of quasars, revealing their structure and environment. Meanwhile, ground-based observatories equipped with adaptive optics can correct for the blurring effects of Earth's atmosphere, providing sharper views of these distant objects. As our understanding of quasars grows, so too does our appreciation for their role in shaping the universe. Quasars in popular culture. Quasars, those enigmatic beacons of the cosmos, are not just astronomical phenomena. They've also carved out a niche in popular culture. Their extreme luminosity, often outshining entire galaxies, makes them a fascinating subject for storytelling and artistic expression. Powered by supermassive black holes at the centers of distant galaxies, quasars are like cosmic lighthouses, their energy output driven by the accretion disks of matter spiraling into these black holes. This process releases immense amounts of radiation, making quasars visible across vast cosmic distances. In science fiction, quasars often serve as plot devices or settings. For instance, in the Star Trek universe, quasars are depicted as dangerous phenomena that can disrupt space travel. The sheer power and mystery of quasars make them ideal for creating tension and drama. They've also been featured in video games, such as Elite and its modern counterpart, Elite Dangerous, where they are represented as exotic and hazardous celestial bodies. These games allow players to explore procedurally generated galaxies, complete with quasars that can be observed or even harnessed for unique gameplay mechanics. Artists and writers have also drawn inspiration from quasars. In literature, they often symbolize the unknown or the infinite. For example, in Arthur C. Clarke's The Fountains of Paradise, a quasar plays a crucial role in the story's technological and philosophical themes. In visual art, quasars are frequently depicted as swirling, colorful phenomena, capturing their intense energy and beauty. Their representation in popular culture not only reflects scientific understanding, but also the human fascination with the cosmos and its mysteries. Moreover, quasars have found their way into music and film. Bands like Quasar, Quasar Smoker, and 30 Seconds to Mars have incorporated the term into their names or lyrics, drawing on the cosmic imagery and energy associated with these celestial objects. In films, quasars are often portrayed as gateways to other dimensions or as sources of unimaginable power. While these portrayals may not always be scientifically accurate, they highlight the cultural impact of quasars and their ability to captivate the human imagination. The impact of quasar studies on astronomy. Quasars are among the most luminous objects in the universe, outshining entire galaxies despite their relatively small size. These cosmic powerhouses emit energy across the electromagnetic spectrum, from radio waves to 10th rays, with some quasars being visible even from billions of light-years away. The extreme luminosity of quasars is attributed to the accretion disks of supermassive black holes, which can be millions or even billions of times more massive than the Sun. As matter spirals into these black holes, it forms a swirling disk of superheated gas and dust. Friction and gravitational forces within this disk generate immense heat and energy, resulting in the brilliant glow characteristic of quasars. The energy output can be so intense that quasars often outshine all the stars in their host galaxies combined. The study of quasars has significantly advanced our understanding of the universe. By observing quasars, astronomers can probe the early universe, as their light has traveled for billions of years to reach us. This provides a window into the conditions and processes that shaped the cosmos in its infancy. Quasars also serve as beacons for studying the intergalactic medium, as their light interacts with the gas and dust between galaxies. This interaction reveals valuable information about the composition and distribution of matter in the universe. Additionally, quasars help astronomers understand the growth and evolution of supermassive black holes, which are believed to play a crucial role in the formation and development of galaxies. Quasar studies have also led to groundbreaking discoveries in cosmology. For instance, the observation of quasars at great distances has provided evidence for the accelerating expansion of the universe, a phenomenon attributed to dark energy. This discovery has profound implications for our understanding of the universe's ultimate fate. Furthermore, quasars have been used to test theories of gravity and relativity, as their extreme gravitational fields provide unique laboratories for studying these fundamental forces. The study of quasars has also contributed to our knowledge of galaxy formation and evolution, as the activity of quasars is often linked to the merging and interaction of galaxies. In recent years, advancements in technology have enabled astronomers to study quasars in greater detail than ever before. High-resolution imaging and spectroscopy have revealed the complex structures and dynamics within quasar accretion disks. These observations have provided insights into the processes that drive quasar activity and the role of magnetic fields in channeling matter into black holes. Moreover, the discovery of quasars with unusually high redshifts has offered a glimpse into the earliest epochs of the universe, when the first galaxies and black holes were forming. As our understanding of quasars continues to grow, so too does our appreciation for their impact on the cosmos and the profound questions they raise about the nature of the universe. Challenges in quasar observation. Quasars are among the most luminous objects in the universe, outshining entire galaxies with their intense energy output. This staggering luminosity is believed to be powered by supermassive black holes, which reside at the centers of distant galaxies. These black holes, with masses millions or even billions of times that of our Sun, accrete vast amounts of gas and dust. As this material spirals inwards, it forms an accretion disk, heating up to extreme temperatures and emitting enormous amounts of radiation. The energy released is so profound that it can be observed across vast cosmic distances, making quasars visible even when their host galaxies are not. Observing quasars presents a unique set of challenges due to their extreme distances and the nature of their energy output. The light from quasars travels billions of light years to reach us, often becoming faint and difficult to detect. Additionally, the intense luminosity can overwhelm telescopes, making it hard to study the surrounding environment or the host galaxy. Astronomers must use sophisticated instruments and techniques to filter out the bright light and gather data on the quasar's properties. For instance, spectrographs are employed to analyze the light from quasars, revealing information about their composition, velocity, and the intergalactic medium they traverse. Another significant challenge is the variability of quasars. Their brightness can fluctuate over timescales ranging from hours to years, making it difficult to obtain consistent data. This variability is thought to be caused by changes in the accretion rate or by instabilities in the accretion disk. To mitigate this, astronomers conduct long-term monitoring campaigns, using multiple telescopes to capture data at different wavelengths. This approach helps to build a more comprehensive picture of quasar behavior. Furthermore, the cosmic microwave background and interstellar dust can distort the light from quasars, requiring advanced data processing techniques to correct for these effects. Despite these challenges, quasars remain a crucial area of study in astrophysics. They provide valuable insights into the early universe, galaxy formation, and the nature of supermassive black holes. By overcoming the obstacles in quasar observation, scientists continue to unravel the mysteries of these enigmatic objects, pushing the boundaries of our understanding of the cosmos. The data gathered from quasars not only enhances our knowledge of the universe, but also drives the development of new technologies and observational techniques. The quest for the first quasars. In the vast expanse of the cosmos, quasars stand as beacons of unfathomable energy. These celestial powerhouses, now known to be powered by supermassive black holes, emit more light and energy than entire galaxies. Their extreme luminosity is a result of the intense gravitational forces at play as matter spirals into the black hole, forming an accretion disk. This process heats the surrounding material to incredible temperatures, generating a brilliant glow and releasing vast amounts of energy. The light from quasars can outshine their host galaxies, making them visible across billions of light years. The quest to understand these enigmatic objects began with their discovery in the 1950s. Astronomers initially identified them as mysterious radio sources, later recognizing their optical counterparts. These early quasars, or quasi-stellar radio sources, puzzled scientists with their star-like appearance and enormous redshifts, indicating their immense distances. The realization that these objects were not stars but rather distant, incredibly luminous entities marked a significant turning point in astrophysics. Their study has since provided invaluable insights into the early universe and the nature of black holes. Quasars are not merely bright. They are among the most energetic phenomena in the universe. A single quasar can emit energy equivalent to trillions of suns. This energy output is driven by the accretion process, where the black hole's gravity pulls in gas and dust, creating a swirling, superheated disk. As this material spirals inward, it releases enormous amounts of radiation, including visible light, X rays, and gamma rays. The jets of plasma that often accompany quasars further amplify their brilliance, stretching across thousands of light years and emitting intense radio waves. The search for the first quasars was a journey into the unknown. Early astronomers, equipped with less advanced technology, relied on radio telescopes and optical observations to identify these distant objects. Their persistence paid off, leading to the discovery of quasars and a deeper understanding of the universe's structure. Today, quasars serve as cosmic lighthouses, guiding astronomers in their exploration of the early universe and the mysteries of black holes. Their study continues to push the boundaries of human knowledge, revealing the secrets of the cosmos one brilliant discovery at a time. As we wrap up our journey into the heart of quasars, let's take a moment to soak in the sheer scale of these cosmic powerhouses. Imagine, if you will, a single quasar outshining entire galaxies, its energy output fueled by the insatiable appetite of a supermassive black hole. These aren't just bright lights in the sky. They're the universe's own spotlights, illuminating the cosmos with a luminosity that can outshine a trillion suns. It's like watching a black hole perform a high-energy dance, with accretion disks and relativistic jets putting on a show that's been traveling across space and time just to reach our eyes. So, what's next on our cosmic adventure? Well, we've talked about the brightest objects in the universe, but what about the darkest? Black holes, those mysterious and enigmatic entities, have so much more to reveal. Join us in our next video as we dive deeper into the abyss, exploring the secrets of black holes and their role in shaping the cosmos. Until then, keep looking up, keep wondering, and remember, every time you gaze into the night sky, you're connecting with the same wonders that have inspired humanity for millennia. Don't forget to like, share, and subscribe for more cosmic journeys. The universe is calling, and we're here to answer.